Good morning, everybody.
Morning.
How is the class doing? Okay, so in the previous class, we talked about, or we introduced the topic of the digital signal processing. We said most of the signals that we're going to be seeing in our real life are going to be signals that we're going to have to be able to process using a computer, and therefore it is very important that we know how to build and design filters. It is very important that we can take any signal and try to plot the spectrum for the signal and understand what that spectrum is telling us about that signal. And we said in this course, we're going to be reviewing the signals and system at the beginning, and then we're going to be introducing the sampling theorem, and then we're going to understand how the signal goes from the continuous time domain to the discrete time domain. We're going to understand the aliasing, anti-aliasing, upsampling, downsampling, and we're going to understand the Nyquist. We're going to talk about Nyquist theorem. So that will give us a very good understanding of how the signal has to be sampled in order to convert it to a digital signal. And then we're going to review the Z transform. I imagine most of us or most of you are familiar with the Z transform, but we'll brush up on it. And it's a very important tool that will help us throughout the semester in understanding the filters and all the different transformation. And then we're going to spend time designing filters, IIR filters, FIR filters, and we're going to look at different techniques that we can use to design these filters. And then we're going to introduce the discrete Fourier transform, and that will tie all the different Fourier transforms together. So we are able to plot the spectrum of a signal using a computer. Make sense? Okay, so with that, in the previous class, we looked at signals. We said we can have a continuous time signal that is continuous in time and can take on any magnitude. And then we can sample that signal, we can quantize it, we can convert it to a digital signal. Now keep in mind, when we look at a digital signal, we have a sequence of numbers. So there is no longer a time coordinate with it. Is that concept clear, or is it not very clear? Like if I have a file that is saved as a digital audio signal, in the file there is no time. There is a time that tells me what the sampling time is, but there's a bunch of numbers. Make sense? We're familiar with signals, being able to plot it versus time. But once it's digital, it's just a sequence of numbers. If you change the sampling time, the whole appearance of the signal is going to change. I can reconstruct an analog signal or a continuous time signal from the digital signal by knowing what that sampling time and converting it accordingly. Make sense? So keep that in mind. It's a little bit confusing, but we'll keep emphasizing it as we go. Okay, so let's look at some basic See, that's why I like OneNote. Okay, so let's go to if you get frustrated seeing this, that you know. Let's look at some basic sequences. So the first sequence, or the first function that we will be seeing, is the unit step function. Unit sample sequence. Where is it?
It's beneath the mouse cursor to the left of the text template. So where you've been clicking on the eraser, look to the left of it.
This one?
Look to the one to
Look
the
to
all
the
the way
left,
on.
3 over.
Left.
Yeah, that,
It's the one that's already highlighted blue.
This one?
Beneath that one.
This one?
yeah.
Perfect.
Now maybe I'll change the font size.
Okay.
Okay.
It's on print.
And basic settings is
We'll figure it out. I mean, I don't want to spend time on it. If we're going to have to use this again, we'll master it before we use it again. Okay, so the first function is the unit sample sequence, which is what we call as delta function or a discrete time impulse. And this is given by delta of n minus n0. This signal is equal to a 1 when n is equal to n0, and it's equal to a 0 elsewhere. How does this signal look like? If I were to plot it, when n is equal to n0, I have a 1. This is n, and this is delta of n minus n0. Now we also, you're probably also familiar with the impulse function in the continuous time domain. How is this different than the impulse function in the continuous time domain? Anybody knows or remembers or want to guess? I mean, it looks the same, doesn't it? But that one, how do we do it? We make an arrow here. But what's the difference between them? Here, it's just a magnitude. The magnitude is equal to a 1. While in the continuous time domain, what was the 1 meaning? What did the 1 mean in the continuous time? What does the 1 mean in the continuous time domain? The area under the function. Does that make sense? The delta, the impulse in the continuous time domain, the width is 0, the magnitude is infinity. But the area was equal to a 1. Make sense? Here, it's much simpler. Just at n0, this function is equal to a 1. Keep that in mind. Anybody not confused? Anybody confused? Okay. The second, as an example, if we have a function that is delta 3 delta of n minus 5, how is this going to look like? When it's going to have a value? When n is equal to a 5 and the magnitude is going to equal to a 3. 3 delta of n minus 5. The second function that we like to introduce is the unit step sequence. And this is given delta of n minus n0 is going to equal to a 1 and a 0, and it is a 1 when n is greater than n0 and 0 elsewhere. So if I were to plot this sequence at n0 and after n0 is going to have a 1, a value of 1, and this is n. Okay. Now, if we are given any sequence, go ahead. Okay. So a unit step similar to the continuous time unit step. U of n minus n0 is going to start at n0, is going to have a value of 1. Okay, if we have any sequence, we can write it as a sum of weighted and shifted delta functions. So I can take any sequence and I can express it as a summation from k equal negative infinity to infinity, the value x of k multiplied by delta of n minus k. As an example, if I have a sequence that looks something like this, at negative 2, it's equal to negative 1. At negative 1, it is equal to a 2. At 0, it is equal to a 1. At 1, it is equal to negative 2. So I have this x of n. I should be able to write this x of n as this summation. What is this x of n gonna look like as a summation of these delta functions? This is going to be a delta, a delta, a delta, a delta. What is this delta going to equal to? The magnitude of it, which is going to equal to a negative 1, delta of n plus 2, plus the second impulse, which is this one, is going to be a 2 multiplied by delta of n plus 1. Plus, what is this impulse going to be?
Delta of n.
Delta of n. Very good. Plus delta of n. And then finally, we have plus minus 2 multiplied by delta of n minus 1. So any sequence, we can always write it as a summation of the magnitude multiplied by an impulse, depending on the position of that signal. Okay. The third function that we're going to introduce is the exponential and sinusoidal signals, sinusoidal sequences. So the general form for this sinusoidal and exponential sequences is x of n equal a multiplied by alpha to the power of n. So we might have a sequence that looks something like this. A multiplied by alpha to the power of n. Now in general, A and alpha are complex. And therefore, I can write A as equal to a magnitude A, e to j phi. This is a polar representation of A. Since A is complex, I can have it as a magnitude and a phase. Also, I can represent alpha as a magnitude of alpha, e to j omega. And we're going to call it omega 0. Make sense? A and alpha are complex, so we can write them like this. Okay. So therefore, I can write this x of n, this sequence, as equal the magnitude A, the magnitude alpha to the power of n, e to j omega 0 multiplied by n plus phi. Can you see it and verify? Alpha is going to be alpha to the n, e to j omega naught multiplied by n. And then I have the phi that's coming from the A. And then I have the alpha to the power of n. The alpha to the power of n. Okay, so this is the general format for an exponential and sinusoidal sequences. Now, as you can see, this sequence is complex, which means it has a real part, it has imaginary part. Okay, so let's look at some special cases. So we're going to call a special case A. And this special case when both A and alpha are real. And therefore omega is equal to omega 0 is equal to phi, and it is equal to a 0. So A and alpha, both of them are real numbers. So in this case, we're going to have the sequence x of n is going to equal the magnitude of A multiplied the magnitude of alpha to the power of n. The exponential term is going to equal to a 1. Make sense? What is an example, a sequence example that applies to this case? If I have x of n equal to a 5 multiplied by 1/2 to the power of n. This is an example of a sequence when both alpha and A are real. How does this sequence look like? What is the sequence going to equal when n is equal to a 0? 5. What is it when n is equal to a 1? 2.5, or 5 over 2. When n is equal to 2, so it looks like a decaying exponential function. It's going to get smaller and smaller and smaller. And when n is negative 1, it's going to look something like this. So this goes from negative infinity to infinity. So this is a special case when both alpha and A are real numbers. Another case, another special case, when alpha is equal to a 1. In this case, x of n is a non-decaying complex exponential sinusoidal sequence. So as an example, if we have x of n equal to a 5 multiplied by exponential of j to the pi over 4 multiplied by n plus pi over 6. How does this look like?
What's the numerators and the exponents?
Exponential j pi over 4n plus pi over 6. What does this sequence look like? It is a 5, and I can write this as a cosine of Euler's formula, a cosine plus j sine. So this is going to be cosine pi over 4 multiplied by n plus pi over 6 plus j sine pi over 4 n plus pi over 6. Again, because e to j x is equal to a cosine x plus j sine x. So what does this signal look like? It's a complex sinusoidal signal. It has a real part and it has imaginary part. What happens if I take the real part the real of the complex sinusoidal sequence is going to just equal to a sinusoidal sequence. So if I take the real of the previous example, if I take the if I take x of n, I take the real of the 5 e to j pi over 4 multiplied by n plus pi over 6 is going to equal to 5 multiplied by cosine pi over 4 multiplied by n plus pi over 6. Again, the real part of this complex sequence is going to be just a sinusoidal sequence. Together? So these are sequences that we're going to be seeing, so we're going to get familiar with them. Okay. Okay, so let's look at some properties of real and complex sinusoidal signal. So the first property is the frequency. We're going to refer to the frequency as omega 0. And later on, we'll explain why we're using this omega versus what is the frequency in the continuous time domain. W. Omega, but W. So we're going to go ahead.
With the lowercase omega.
Yes, with the lowercase. So this is our frequency. What is the units for this frequency? It's going to be radian per sample, or radians per sample. What is the frequency of a continuous time signal?
Per second.
Radians per second. Excellent. Because we're going to have W multiplied by T. As we're going to see here, we're going to have W multiplied by N. And then we have a phase, which is phi. Okay. Let's look at the relationship between the discrete time and the continuous time frequencies. So let's say we have a continuous time signal, x continuous of t equal to cosine omega 0 multiplied by t plus phi. Again, omega 0 radian per second. We're already familiar with how this signal looks like. This is a sinusoidal signal. It might look something like this. Agree? So what we're going to do, we're going to take this sinusoidal signal and we're going to sample this signal. So I'm going to come here to this signal and I'm going to take samples of this signal. How often I'm going to take samples? Every t seconds. So at 0, I take a sample. At t, I take a sample. At 2t, I'm taking a sample. At 3t, I'm taking a sample, and so on and so forth. Now, how many signals we have on the board? We have 2 signals, one in black, that is continuous time signal, and one in red, that is a discrete time signal. So the continuous time signal is the one in black, that is x continuous of t, and the other sequence is the one that is in red, and we're going to refer to it as x of n. What is the expression for x of n in terms of x of t? Want to make a guess? Of course, people who took signals and system last semester should answer it without even thinking. What is x of n in terms of x continuous of t? No, much simpler. I mean, you have this sequence. If I want x of 0, what do? I do to x continuous, I substitute as 0. If I want x at 1, what do I substitute here? X at what time? At t. If I want x at 2 here, the second sample, it's at 2, what do I have substitute?
X is capital T?
X of 2 multiplied by capital T. Yes. So therefore, what is this xn of xn is going to equal to? Is going to equal x continuous of n multiplied by t. Agree, everybody? Straightforward. X at 0, x continuous at 0. X at 1 is going to equal x continuous at t. X at 2, x continuous at 2 multiplied by t. Okay. So therefore, if I do that, if I substitute in x continuous, what is x of n going to look like? It's going to equal cosine omega 0 multiplied by t multiplied by n plus phi. How did I get this? Just plug in, and instead of t, n multiplied by t. If I plug in n multiplied by t, I'm going to get omega 0 multiplied by n multiplied by t plus phi. Okay. Now if I come here, I'm going to write this as cosine omega 0 multiplied by n plus phi. What is this omega 0 equal to? The frequency in the discrete time. But what is it equal to in terms of this expression? Omega 0 multiplied by t. Agree? Okay. Okay, now this frequency is our discrete time frequency. So this omega 0 is our discrete time frequency that we said the units for it are radians per sample. This is our continuous time frequency. Okay. Now it is very important. We are familiar with this frequency omega 0 in the continuous time domain. Now we're going to see in the frequency domain, things are going to be slightly interesting. So first of all, if I take a sequence x of n equal e to j 2 pi multiplied by n, what does this sequence look like? I can write it as cosine 2 pi multiplied by n plus j multiplied by sine 2 pi multiplied by n. What is this sequence going to look like? Anybody want to guess? Plug in any value of n. What is it going to always be? 1. This term is going to always be 0. This term is always going to be 1. So this is equal to a 1. What is omega 0 equal to? Omega 0 from here, what is it equal to? 2 pi. So when omega 0 is equal to 2 pi, I'm getting a sequence that is all equal to a 1. Agreed? Let's take another sequence. X of n equal e to j 0 multiplied by n. What is the frequency here? What is omega 0? 0. What does this sequence look like?
1.
A 1. See it? I have a frequency here that is 2 pi to give me a sequence of a 1. I have a frequency here that is a 0, still give me the same signal. So here, omega 0 is equal to a 0. Make sense? Now this is interesting, and this is different than continuous time signals. How is that different than continuous time signals? In continuous time signal, if I change the frequency, I get a new signal, isn't it? Here, I'm changing the frequency, I'm getting back the same sequence. Okay, so therefore, we're going to state that omega 0 is indistinguishable from omega 0 plus 2 pi multiplied by a k. And this is very important, and we will see it throughout our course, so it will be familiar to everybody. Omega 0, the frequency in the discrete time domain, is indistinguishable from that frequency plus 2 pi multiplied by any integer. Sorry?
That makes sense with gradients.
Yes. So if I take a sequence as an example, x1 of n equal e to j omega 0 multiplied by n, x2 of n equal e to j omega 0 multiplied by n plus 2 pi multiplied by k. What is the difference between these two sequences? Nothing. Both of these sequences are the same. And why is that? Because I can write this as equal to, this is equal e to j omega 0 multiplied by n multiplied by e to j 2 pi. What am I missing here? I'm missing the j. 2 pi multiplied by k. What is e to j 2 pi multiplied by k equal to? A 1. So this is the same as this. Does that make sense? Everybody? Keep that in mind. Okay. So if you look at an example, if I have a sequence x3 of n that is equal e to j omega 0 multiplied by n plus 6 pi multiplied by n, what is this sequence equal to? It's going to equal e to j omega 0 multiplied by n. As an example, if I have a sequence x of n equal e to j 7 over 2 multiplied by pi multiplied by n, what is this sequence equal to? Give me two sequences that will have the same value as this sequence. Okay, I'll give you and you tell me why it is the same. Why are all these sequences the same?
Because you're adding or subtracting 2 pi.
Excellent. Because this 7 over 2 is 3.5 pi. I can add 2 pi, subtract 2 pi, it will be the same. If I subtract 2 pi, I'm going to get e to j negative 0.5 pi. If I added, if I subtracted 2 pi, then I'm going to get e to 1.5 pi. Make sense? Everybody? Okay. Now, whatever applies to this exponential, complex exponential, applies to a sinusoidal signal. So this is the same as saying, if I have x of n, that is equal to cosine 7 over 2 pi multiplied by n. This is the same as cosine negative pi over 2 multiplied by n, which is equal to cosine 3 pi over 2 multiplied by n. All of these signals are the same. And you should be shocked. Anybody not shocked? Because all what we're familiar with, you take any sinusoidal signal, you change the frequency, it's a new signal. All of a sudden, I'm telling you, this frequency, this frequency, this frequency, all these signals, if you go to MATLAB plot them, they are going to generate the same sequence, the same signal. Make sense? Okay. Okay. So therefore, when we study discrete signals or digital signal, we're going to restrict our frequencies to the range from 0 to 2 pi or from negative pi to a pi. Omega 0 is going to be between negative pi and pi, or omega 0 between 0 and 2 pi. Again, why is that? Why?
Because negative pi is the same as pi.
Because we're changing it from negative pi all the way to a pi. Does that make sense? So we're covering from 0 to, I mean, either this or this. You can pick whatever you want. The range is from 0 to a 2 pi. This is the only range of frequencies in discrete time signals. The sequence, this is the range of frequencies a discrete time signal can take. And again, this is different than a continuous time signal where the frequency can go any value. Any different frequency, it's a new frequency. Here, there's a limited range of frequencies that the discrete time signal can take on. Okay. So I'm going to highlight that in red, that this is different than continuous time signals. If I have a continuous time signal and I have x1 of t equal to cosine pi multiplied by t, then omega 1 is equal to a pi. If I take another signal x1 of t equal to cosine pi plus 2 pi multiplied by t, what is this signal going to be? How is this signal related to this signal? They're not the same.
Oh, it's.
Because it is a continuous time signal. Make sense? So this is going to have a frequency that is pi. This is going to have a frequency, omega 2, that is equal to 3 pi. These two signals are different. This is going to have a signal that looks like this. This is going to have a signal that is 3 times the frequency. However, if this was a discrete signal, x of n and x2 of n, they're going to be the same. Make sense? Everybody? Okay. Okay, now if I have a sinusoidal signal, whether it is real or complex, not all sinusoidal sequences, as we will see, are going to be periodic. And also, this is different than continuous time signals. It's going to be periodic if and only if there exists integers n and k such that omega 0 divided by 2 pi is equal to k over n. Therefore, ratio of integers. So a sinusoidal signal, again we're referring to the discrete time sinusoidal signal, is going to be periodic only if there exists two integers where if I take omega 0 divided by 2 pi, is going to be an integer over an integer. And we call n the fundamental frequency, the fundamental period. And therefore, x of n is equal to x of n plus capital N. Okay, so let's look at some examples and see whether a sequence is periodic or not. What is a periodic signal? A signal that repeats itself, yes. So if I have a sequence, e to j 4 pi over 3 multiplied by n. Now again, I'm going to be using complex exponential or a complex sinusoidal or sinusoidal. Both of them mean the same thing. Whether I've written this as 10 e to j 4 pi over 3 or cosine 4 pi over 3 multiplied by n, when we're looking at the frequency, they have the same frequency. Make sense? Okay, so how do we determine if this sequence is periodic and what the period is? I'm going to take omega 0. What is omega 0 equal to? 4 pi over 3. Therefore, I'm going to take omega 0 divided by 2 pi is going to equal to 4 pi divided by 3 divided by 2 pi. And what is this going to equal to? 2/3. Is this an integer over an integer? Yes, it is. Therefore, this sequence is periodic. What is the period of this sequence? N is equal to a 3, which means x of 0 is going to equal to x of 3. X of 1 is going to equal x of 4. Make sense? Everybody? X of 0 equal to x of 0 plus 3. X of n is equal to x of n plus 3. Okay. Let's take another sequence. Cosine 5 multiplied by n. Is this sequence periodic? Yes or no? Omega 0 is equal to a 5. Therefore, omega 0 divided by 2 pi is equal to 5 over 2 pi. Is it periodic? No. It is not equal integer over integer. Is anybody thinking, oh, what happens, why don't we write pi as 22 over 7? Anybody is thinking that? Good. Yes, no? Why can't that not solve the problem? You know what I'm saying? I mean, somebody, what is it?
That's only an approximation.
Excellent, yes. I mean, a pi, we can approximate it by 22 over 7, but that's just an approximation. Okay. So not integer over integer. And therefore, not periodic. Now this, I don't know if it is confusing or shocking to anybody, that you have a cosine 5n that all our life will think it's periodic. All of a sudden, it is not periodic. It is not. And again, you can, we'll make it in the assignment, you can go plot it in MATLAB and you're going to see it's never going to repeat itself. Make sense? I mean, it's going to still look like sinusoidal, but what's going to happen? There is no period where it's repeating at the same period. Does that make sense? So you might look at MATLAB, I mean, you might go to MATLAB and plot it, it's like, oh, wow. He said it's not periodic. Looks periodic to me. But then what is it you're going to do? You're going to zoom in and realize, no, it's not periodic. Okay. Okay, so what happens if we add multiple sequences together? And these sequences are periodic. So if we have a sum of periodic signals is periodic with period equals the least common multiple of individual periods. Make sense? So let's look at an example. If I have x of n equal to cosine 3 pi over 4 multiplied by n plus cosine 5 pi over 3 multiplied by n plus pi over 2 plus cosine 2 pi over 3 multiplied by n. I want to determine the period of x of n. How we determine the period? We're going to find the period of individual components, and then we're going to take the least common multiple of these components. So for the first component, n1, we're going to take the 3 pi over 4 divided by 2 pi. What is this going to equal to? A 3 over 8. And therefore, what is n1 going to equal to? 8. The period of the first component is 8. What is the period of the second component? 5 pi over 3 divided by 2 pi, which is going to equal 5 over 6. Therefore, n2 is equal to a 6. The period of the third component, n3, 2 pi over 3 divided by 2 pi, which is going to equal to 1 over 3, and therefore n3 equal to a 3. Okay, so if you have a pattern that repeats every 8, and you have another pattern that repeats every 6, and I have a third pattern that repeats every 3. Okay, probably my graph made things even more confusing than they're intended to. How often does this pattern repeat? You cannot tell by the graph, but if you go home, just plot it in a nicer graph. If this repeats every this has a length of 8. This has a length of 6. This has a length of 3. How often this whole pattern repeats if I were to keep plotting it?
Is it 3 times 6 times 8?
No, it will be a repeat sooner. Well, that will repeat it. But what is the smallest number where they will repeat?
24
24. Why is 24?
is the least common multiple.
Least common multiple, yes. Without relying on this graph altogether, you can just calculate the least common multiple of 8, 6, and 3, and this is going to equal to a 24. So if this is 8, 8, then you're going to see that this pattern is repeating. Can you see it with a little bit of imagination? With a lot of imagination? Okay. I mean, if we had the one note, we could have plotted it nicer. But so every 24, this pattern is going to repeat, etc. Okay, let me save all this before we lose it. Okay, is that clear? Makes sense? Okay. What is the maximum frequency that a discrete time signal can take? And that is going to be omega 0 equal to a pi. Why is this the maximum frequency? Because if I have a sequence x of n that is equal to e to j pi multiplied by n. What is this omega 0 here? A pi. Or if I have a sequence x of n, that is equal to a cosine of a pi multiplied by n. Both of these have omega 0 that is equal to a pi. And what we're saying is this is the maximum frequency you can have. Okay, why is that? If I were to plot this sequence, how does this sequence look like? What is it going to equal at 0, at 1, at 2, at 3, at 4, at 5, etc.? This is x of n. What is x of 0? 1. What is x of 0? Is going to be cosine of a 0, which is going to equal to a 1. What is x of 1? What is it? Negative 1. X of 2? 1. 3, negative 1. 4, 1. 5, negative 1. Agree? Now, if the signal is changing this much, it's going from 1, the next time is going to the extreme of that one, negative 1, to the extreme to the 1, extreme negative 1. Can the signal change any farther than this? Can you think of any more change than going from a 1 to a negative 1? No. So this is the maximum frequency. The maximum change you can have in your signal is a signal that's going to look something like this. Make sense? And that's why the highest frequency, the maximum possible frequency of a discrete time sequence is going to equal to a pi. Together? And again, this is different than continuous time signals, where you increase the frequency gets higher. Here, there's a maximum frequency, which is equal to a pi.
I have a question. So, if the maximum possible frequency is pi, then how is it possible to restrict the frequency between 0 and 2 pi?
We can have a sequence between 0 and 2 pi. The frequencies can be between 0 and 2 pi. But among this sequence, the highest frequency is the pi. Does that make sense? It's confusing, but you see that's why it's different than continuous time signal. The range of frequencies, we can have a valid frequency from 0 to a 2 pi. What is the highest frequency there? The pi. Still confusing, isn't it? Say yes so I can explain it. Otherwise I will move on. In the continuous time frequency, where is the low frequencies here? Where is the low frequencies? This is the low frequency, isn't it? Where is the highest frequency? The farther I go from 0. When I go to infinity, that's the highest frequency. Make sense? And discrete time signals, if I were to plot the frequency from 0 to a 2 pi, where is the highest frequency? It's here. Make sense?
Yeah.
So if I'm designing a high-pass filter is going to look something like this. This is a high-pass filter. Why? Because this is the high frequency. I'm going to have this frequency go through. Is that clear, everybody? I mean, very good question. In discrete time, this is low frequency, this is low frequency, even though this is happening after. But it's different than continuous time. This frequency is a low frequency. This is a high frequency, low frequency. We go to a high frequency, then we go back to a low frequency. Okay. Again, these things will become hopefully more clear and become almost intuitive with time, but for the time being, it's fine if they're confusing, because that will have you always paying attention to it. But again, with time, these will become more clear. Okay, so this is the maximum possible frequency. What is the minimum possible? What is the period of this signal? 2. So for this sequence, n is equal to a 2. And therefore, x of n is equal to x of n plus 2. What is the minimum possible frequency? Who wants to guess? 0 or 2 pi. 2 pi is just as low frequency as a 0. Minimum frequency is omega 0 equals 0 or 2 pi. In this case, there's no oscillation whatsoever. So if I have a signal x of n equal to cosine 0 multiplied by n, or if I have a sequence x of n equal to cosine 2 pi multiplied by n. How do these two sequences look like? A constant. The same, constant. At 0, it's equal to a 1. At 1, it's equal to a 1. At 2, it's equal to a 1. 3, 1, 2, 3. This is n. Same thing. At 0, it's equal to a 1. At 1 is equal to a 1. 1, 1. And this is n. Make sense? And that's why it's very low frequency. What is the frequency here? What is the frequency represent? How fast the signal is changing? Is the signal changing? 0. There's no changes. The frequency is 0. And this is the new thing where even though it is a 2 pi, it's still the frequency, that frequency is low. The signal is not changing. Together? Everybody? Okay. Okay, with that, I think we have enough of signals. Let's briefly review the discrete time systems. So if we have a discrete time system, we have an input, we have a discrete time system, we have an output, y of n. Y of n is equal to the response of the system to the input x of n, or we can say x of n is going to give me an output y of n. Together? What is this discrete time system going to look like? It might look like an algorithm on the computer. Makes sense? And will become more clear how this. It could be also, I can build it using a circuit, but I can also build it using a microcontroller, a microprocessor. Again, will become clear as we go. But unlike the continuous time system, where this is going to be a physical components that are applied, here this could be just a sequence that or an operation that I'm going to do on the sequence x of n. I could have a system here where the output is equal x of n minus x of n minus 1. So I could have a discrete time system that might look like this. Y of n is equal to x of n minus x of n minus 1. So this might be a filter where all what the filter is going to do is going to take the current input and subtract from it the previous input. What do we call this from those who just took systems. Start with difference equation. Difference equation. This is one of the representation of the system. I can use a difference equation. Okay. So what are the properties of systems that we know of? We can have a system that has memory or a system that is memoryless. What is a memoryless system? Anybody? The output at any time n will depend on when? On the input at that time. If the system has memory, then the output at any time will depend on the input at that time, in the future, in the previous time. So it has to have a memory. So as an example, y of n equal 5 multiplied by x of n plus 3. Is this with memory or without memory? Without memory. It's memoryless. As an example, y of n equal to 5 multiplied by x of n minus 1 plus 3. Is this with memory or without? With memory. Okay. Another classification is whether a system is linear versus non-linear. Who still remembers the difference between a linear and non-linear system? Every time I explain this, I ask the students to remember it. And what do the students do? They decide to be memoryless. So the system is going to be linear. If I applied x1, I get y1, x2, y2. Then if I apply to it a multiplied by x1 plus b multiplied by x2, what should the system give me? A multiplied by y1 plus b multiplied by y2. So the linear system satisfies homogeneity and additivity. So if I applied x1, got y1, I probably should add another block. If I applied a x1, I should get a y1. This property is homogeneity. Adding them together is additivity. So I don't know if I made it now more confused. So there is two properties here. Homogeneity, which means that x1 gives me y1, ax1 is going to give me ay1. Additivity, which means if I applied x1, applied x2, got y1, y2. If I apply x1 plus x2, I'm going to get y1 plus y2. If I add these together, I can I think the logic behind this tool that I'm using is it does not want you to make any mistakes. Pay attention so you don't have to use the eraser. So if we added these together, we're going to get the superposition. Okay, as an example, if I have y of n equal to x of n squared, is this linear or not linear? Non-linear. y. Because if I have x1 plus x2 squared, it's not going to equal x1 squared plus x2 squared. Y of n equal to 5 multiplied by x of n. This is a linear system. What about 5x of n plus 3? What is it? Nonlinear. 5x of n plus 3. Linear or not linear?
Is the 3 like a bracket?
No. Here. Y of n equal 5 x of n plus 3. Nonlinear. Why is it nonlinear? Anybody remembers? Why is it linear? Is it linear? Nonlinear. Excellent. Because if I applied x1, I'm going to get 5x1 plus 3. If I applied x2, I'm going to get 5x2 plus 3. If I add them together, I'm going to get 5x1 plus 5x2 plus 6. But if I apply x1 plus x2, I'm going to get 5x1 plus x2 plus 3. You see it? Everybody? Just like if you were to go to a bank, and every time you open an account, they're going to give you $10. If you have $100, you can go open an account. They're going to give you $10. You're going to have $110, isn't it? Then you're smart. You say, oh, every time I open an account, they give me $100. Let me open 2 accounts. Here's $50. Open an account. They're going to give you $10. Here's another $50. Open an account. I'm going to get $10. How much I have now? 120. In the previous case, how much I had? 110. Nonlinear. So it's very similar. I'm giving you 6 on top of 3 of your inputting. If you input individually, you're going to be getting a 3 and 3, which is 6. But if you put them together, I'm only giving you 3. Who's going to remember that? At least till next class. Okay, I mean, please try to remember it. This will be an excellent interview question. What is a linear system? Like these things you should be always prepared to answer, even if you're done with the class. Okay. What is a time varying versus time invariant system? Time varying versus time invariant. If I apply x of n, I get y of n. If I apply x of n minus n0, what should I get at the output? The same output shifted by the same amount of time. Shift the input is going to result in the exact same shift of the output. Okay. If I got if I applied x of n minus n0 and I got y of n minus n0 minus 1, is this going to be time varying or variant? Variant. Because the condition has to be n0. Not only I should get the same output, I should get the same output with the same shift. So this will be time varying. Sounds good? Okay, I'll stop here.